perish all the same.
Yesterday, I talked to you about the chemistry in the troposphere that you had to understand as modelers and as people doing observations. We've had some very interesting talks on satellite measurements this morning and also on the details of how you get chemistry into models and how you represent processes in models in terms of some of the mathematics. I want to step out again now and try and give you perspective of a modern issue that we need to address with respect to the sort of science that we do. I'm going to give you very much kind of a top-level overview. In a way, what I'm trying to do is take some of the sort of knowledge that we've got so far and say, well, how can we apply this in a scientific issue? I'm going to talk a little bit about air quality, which I guess is the question of how clean is the air that we breathe. So, to start, a picture. Number one thing about this picture, do not try and take pictures of grey things on a grey background. But nonetheless, that's what my workers did. What are you looking at? Any idea what you're looking at? Filters. Filters. What's on the filters? Particles. That's actually the air in Leicester, the city I come from, over the last couple of weeks. And what you're looking at there is just drawing air through a filter, as you say, and you look at the particles that are in that air. And you've already heard about that. And if any of you came last night to Kathy's excellent lecture in the town hall in French, she talked extensively about how those particles enter our lungs and cause damage. And that's the basis of air quality, the way that pollutants interact with human health, ecosystems and buildings to cause damage. And you can see there's a lot of information in those filters, because you can see there are, on some days, much more. The far right one, oh, I've lost my pointer. The far right one on the end there is actually a blank. That's what it looks like without. Can I ask somebody who's a master of these things to open it for me? I failed. The one on the far right of there is a blank. But you can see there's a great deal of variation. There's a great deal of variation with those days. And I want to think about a little bit of some of the things that drive that during the course of this talk. So.
I'm an experiment.
Thank you, John. All right, there we go. So air quality. Air quality is considered to be a basic requirement of human health and well-being. However, air pollution continues to pose a significant threat to health worldwide. That's a statement by the World Health Organization. Does everybody know what a global commons is? Everybody know what a global commons is? I learnt this phrase recently, and somebody said, yes, you've got to be very careful about the global commons. And I'm like, the global commons? It belongs to everybody. Air actually belongs to everybody. It's a resource that we all use. In fact, we all use it for free. We don't pay for it, and we all share it. So there's a very important kind of concept there in global commons, and there are many other global commons. The oceans are the same, but yet we use the resources in the oceans. But they are a shared resource that we have. And the air that we have is a shared resource, is a global commons, and we have to think about treating it as a shared resource. So here's how the media sometimes portrays this. If you want protection against pollution, wrap yourself in cling film and don a gas mask. Now, I don't see many people in Anglais Barretts dressed like this, walking down the street, responding to the challenge of air quality. Yet the media way of dealing with this is for this sort of extreme view. Yet there is a real impact of this. Now, I just have to have I happen to have in this presentation the UK numbers, but these scale up roughly linearly across the EU. Air pollution costs the UK, which is a population of 65 million or so, around £15 billion a year. I'm sorry we didn't join the euro. We're very unlikely ever to join the euro. It's about 1.18 pounds to the euro at the moment. Or if you buy it at the airport, it's about a 1-to-1 ratio. So it's about 15 billion euros. It's interesting to kind of think about the context of health costs. Because obesity is a very big issue that was in the media a lot in the UK. Yet obesity only costs the UK 10 billion per year, yet you hear a lot more about it. And I think that tells you something about the perception of air quality. Actually, in surveys about air quality, many people think it's the #1 environmental issue because it affects people here and now. They have a much more greater problem with climate change, which is somebody else's problem. It's going to occur sometime in the future. But actually, when you survey people about their environmental worries, air quality is often there. Yet politicians have a great difficulty in dealing with it because of the immediacy of solutions. And there are some more evidence here from a recent report stating that poor air quality reduces the expectancy of everyone in the UK by an average of 7 to 8 months, and up to 50,000 people a year may die prematurely because of it. And that's very actually similar to the numbers that you'd find for a country the size of France as well. They're very similar types of numbers. And actually here's a statement from this parliamentary committee. Despite these facts being known, air quality is not seen as a priority across government, and the UK is failing to meet a range of domestic and European targets. And that's actually true not only of the UK, it's true across a wide range of Europe. And that's how the media portrays it. And this is the interesting one on the bottom here, actually. It's worth noting. Here we've gone from 15 to 20 billion, which gives you an idea of what the uncertainty is this. And we face we face a £300 million EU fine. Now that concentrates politicians' minds. Now if you're going to get fined 300 million, now we would have a long debate about whether the EU will ever fine anybody, but actually if there is, that does concentrate politicians' mind, and they do want to know what you're going to do about it. So that's a little cursory kind of look at the top level political drivers for this. So let's just kind of regress. Air quality impacts a number of contemporary issues, human health, and there was a brilliant talk last night by Kathy on this topic. I'm not going to kind of repeat it, but to note that it does impact respiratory, cancer, COPD, allergies. Probably less talked about is ecosystem impact, particularly things like ozone will reduce crop yields, and we lose across Europe a lot of money from the reduction of the productivity of our ecosystems through direct impact of air quality, but also through continuing acidification and eutrophication of those systems as well. It does also impact national heritage and the way that we have to look after our buildings. You do get leaching of stone, etc. And also it does have a role in regional climate. Aerosol and ozone exhibit a strong regionality in climate. So it's a very pervasive issue, and I'll come back to the links between air quality and climate a little bit later in my talk. There's been a lot of interest in thinking about the role that air pollutants have to play in the climate story. Just to remind ourselves where we are in the atmosphere, John mentioned this as well. We're very much talking really about the bottom. When we talk about air pollution, we're really talking about mainly human exposure and crop exposure. So actually, according to the EU, that's air pollution at a height. The average height of the European citizen is about 1.2 meters. So we're all about kind of that sort of mouth level is where we're worried about the air pollution. I'm not going to repeat the mantra to you, but to remind you that actually what I'm talking about is the very same sort of thing that we're talking about today. Emissions of air pollutants, most of which comes from the surface. Chemical transformation, and I talked yesterday about primary and secondary pollutants and their impact, and then how fast they're removed from the system. And you've got to remember, they're the three things that you've got to get, lest you forget, the only one thing you have to remember from this summer school. If we look at that in a more complex way, a more complex representation, thinking about really humans in the centre, we then have this now, when we're talking about air quality, this huge range of sources, the natural sources from soils and biogenic, a whole range of sources from agriculture, from industry, from automobiles. Then we've got the transport and transformation in the atmosphere. This is a more complicated version of my three things. And also its impacts here in black, just a wider version of the ones that I've said, and the loss processes in blue there. So we're dealing with my three steps in a much more complex interaction. And I think actually the realization for Earth system science is that we have to move away from the idea as humans as a passive observer of environmental change. You know, in a way, humans are the only species on Earth that can change the very environment that supports them. There is no other species or animal on Earth that can change its environment in order to actually make it worse for itself, so that it could actually make itself extinct. So we have to really move, and there's a paradigm shift, I think, going on in terms of looking at the way that humans are really the center of the system, the forcer of change and the feedbacks on humans. And there's a program called Future Earth, which I'll talk a little bit about tonight when we talk about international programs, which is moving in that direction. So when we talk about air quality, what are the major components that we're talking about? We're talking about ozone, which we talked a lot about yesterday, nitrogen dioxide, NO2. We're talking about particles, fine particles, and I'll talk a little bit more about those particles in an air quality context. And then we're talking about other pollutants as well, carbon monoxide, and also there's a whole range of metals, which I won't really talk about today, and some hydrocarbons such as benzene and 1,3-butadiene, which are controlled under air quality legislation. And we tend to call these the criteria pollutants. They're all ones that have clear health impacts and that we can trace through. So they're the major set of ones. Probably the only one that's really missing off there is sulfur dioxide as well. But that's very much a problem that's under control, at least in Europe. So, to my first step, emissions. Here are some emission maps for these pollutants from nitrogen oxides and PM10. What do these maps tell you, other than the UK is an island? Which I think I know. Pardon?
Where the cities are?
It tells you where the cities are, doesn't it? It tells you where the economy is. So actually, air pollution is a very interesting marker in itself. You look at the emissions. I mean, if you look at the emissions of nitrogen oxide, you could virtually pick out the UK road network. You can tell where the major motorways actually are. So that tells you something about the emission sources. Also, you could take away from this, there is a spatial distribution of these sources. I mean, it's a fairly obvious thing. Emissions are spatially distributed. I mean, I'm not telling you anything that's rocket science there. But when it comes to air quality, if I wanted to go somewhere to live in the United Kingdom away from air quality, where would I live? Scotland. Now, you might say, why am I saying this to you? That is a question that people email me. I get emailed. I get emailed quite a lot. I'm the chair of the Government Science Advisory Committee on Air Quality, and I get emailed, I'm really worried about air quality, where should I live? And my answer to them is Scotland. If you want to get away from it, go and live in Scotland. Actually, I say to them, go and look at the data online. It's not for me to recommend where to go and live. You have to be a bit careful to tell people where to go and live. But you can see them, the emissions, you can see the spatial distribution. Here's NOx and here's PM, and they're in fact, they do have very different sources, and you can see that in their spatial distribution. We can actually see this pollution from space, and John will talk a little bit more about this. I'm sorry, these are Heidelberg maps, John. But you can actually see it from space. Where wouldn't you live if you're worried about NO2 in the world? Europe, Belgium. USA, China. That's the Veld in South Africa. If we zoom in a little bit nearer to home, this is kind of a picture of NO2 over Europe. How good's your geography? Anybody a geography student here? Ah, okay, right. Let's go. What's this city here? Naples. Yeah, Napoli. Athens, yes, well done. There's a Greek in the audience. Istanbul. Ankara. The Po Valley. Where not to live. Northern Italy. We know that one, don't we? Marseille. Right. Now the hard ones. You've done the easy ones. Upper Silesia. No. What about this one in here?
Munich.
Munich, yes. That's the kind of Munich conurbation. What's this one up this side here?
Zurich.
No, it's further north.
Right, the North Rhine-Westphalia.
No, the North Rhine-Westphalia's up there, isn't it?
Oh, this is the Rhine Valley.
That must be the Rhine Valley.
Lake Constance.
Lake Constance. So, now, look at this bit here. Now, what you can clearly see, the pollution flowing out of this area into the United Kingdom. Look at the flow of this stuff, pouring out of this region. Unfortunately, the prevailing wind direction is this way. But this is the Nox heart of Europe over here, and images from an experiment that John was the leader on, Schiermacher, actually appeared on Dutch bus shelters during an electoral campaign. There's a guy from Holland at the back here, so the Netherlands at the back here nodding. So actually, these images have real impact. This is air pollution from space. So nonetheless, what you can see there is that actually pollution pervades across Europe. NO2 exceedances and fine particle exceedances are the prime two exceedances in terms of air quality across Europe. And you're very good on your geography as well. Now, I started off this with a sort of very grim tale. You know, air quality is terribly bad for you. You know, and you've heard yesterday again. You know, if you go back to the smogs of the late 50s, you know, many people died essentially over a week. And air quality is a success story in some respects. If you look at the emissions of many of the primary pollutants going into the atmosphere, if you go back just over a couple of decades, they have markedly decreased. So we have reduced it. And actually, if you look at some of the pollutants that have changed over that time, some of them have decreased. You look at nitrogen dioxide, it did decrease and then it's kind of flattened out. If you look at some of the other pollutants, they have decreased, have gone down from about 30 micrograms per meter cubed to around 15 micrograms per meter cubed. So there is a success. But it's all not very easy though, because if you look at something like ozone, this is in a city, in Birmingham in the UK, actually it's gone up. And I talked yesterday about the non-linearity in the chemistry, that you might not always be able to reduce the pollutants. You might actually increase the efficiency of the system to make ozone. So there's a very complicated story that we need to pull apart in air quality. And you've got to think about the way that it actually all works. What you have here is impact-driven. The reason why people primarily want to deal with air quality is that it shortens people's life. We never say kill. We never say kill. Kill is not a nice word. We talk about deaths brought forward. So we recognize that everybody's going to die, and we recognize that what air pollution will do is bring that death forward. So months of life lost is another sort of metric that we use, but we recognize that it will hasten your demise. So we have impacts here. And we then put on policy. The major policy knob that we have, the major policy tool that we have is to control emissions. One of the biggest things that we've done to do that, if you go back over the last 10, 15 years, is we put catalytic converters on the back of cars. And I'll talk a little bit about Euro 6 standards later. And that's reduced end-of-tailpipe emissions greatly over that period of time. Once we control those emissions, we make observations of the air quality, and there's various rules which I won't bore you with as to how you make those observations, and then you can assess the impact using those observations on health, and then decide whether your policy has been a success. And that's really the sort of model that we have for air quality. Okay, so what I thought I'd do, rather than trying to churn you through a vast amount of chemistry on air quality and where it all comes from, what I thought I'd do is I'd give you more a topical overview of some of the issues in air quality that are coming now, which are at the forefront of both scientists and policymakers' things, to kind of give you an idea of some of the range of science problems and policy problems that air quality presents. I don't know if any of you remember the heat wave of 2003. That's one of the hottest summers that we've had. During that heat wave, there were around 2,000 excess deaths in the UK, and 700 of those were attributable to the high levels of ozone and PM10. And this is a picture that we did at the time of ozone, which was some of the highest ozone. Also, it was also some of the highest temperatures ever measured in the UK, a smidgen under 40 degrees on the south coast in the UK. And that was 20 to 40% of all the excess deaths in the UK. And that was part of a much wider European problem. This is a map from a French model of the same sort of period. You see there's these huge and high levels of ozone. And over Europe, it was estimated between 22,000 and 44,000 excess deaths during that period. Now, it's quite complicated to pull this apart because you get the heat effect as well as the air pollution effect that goes alongside. You get also the question of vulnerable populations. Older people tend to be more vulnerable to both heat and to air quality, air pollution. So that was a very massive event, probably our equivalent in some respects of the great smogs of the late 50s. You might say, well, why have I brought this to the fore? What you know, that was that. Well, that reoccurred again in 2006, not quite the same scale. And one of the things that's predicted as we move into the future is that these sort of events will occur more often. Now, if you're British and you lived through last summer, where it rained continuously from May till September, you might wonder about predictions. But if any of you are climate modelers, you're responsible for those predictions. Get them right, you know. But nonetheless, it is predicted that as the climate changes, we will get, in Northwest Europe in particular, more of these type of events. And therefore, they will have a direct impact on air quality and therefore on human mortality. That does bring us nicely to the linkage between air quality and climate. Here's I can't actually believe I'm probably the first person to show this figure. I thought it was obligatory to show it at every meeting that everybody goes. And you're probably, you're very used to looking at that figure, and you've looked at it millions of times, and you know it all off by heart, and no doubt shortly they will produce another one which will look slightly different, and that'll keep us going for the next number of years. Probably, when you think about looking at this figure, you go, yes, I'm very familiar. There are some long-lived greenhouse gases, CO2, methane, N2O, halocarbons that are in there, and they cause the bulk of this positive radiative forcing. Probably what you're not so, you're probably actually familiar with what all these boxes are, but probably not so familiar with the sources of those. Because there is significant climate forcing, particularly in this area here, by these chemically active species. And actually, many of the air pollutants that I'm talking about are actually also chemically active. And there's been a great sort of push in recent times to think about whether we can get short-term relief based on still having to reduce the long-lived greenhouse gases, but we could actually make our 2-degree target if we reduced our air pollutants, if we can get the change in air pollution. Probably a better way to think about that is if we just repartition this graph to look like this, where we have the aerosols here doing all the cooling and all the greenhouse gases together doing the warming. So actually, if you think about it, the air quality regulated gases, which are most of the aerosols, are the largest factors offsetting the greenhouse gas forcing. So when we implement air quality policy aimed at human health, we're going to be reducing this side of the equation. We're actually going to accelerate the effects of climate change. There's a very famous paper written by Frank Lass and John Seinfeld called The Bumpy Road to Recovery, which says you're going to get this short-term acceleration before you get the long-term effects that kick in. And these aerosols in particular are things like sulfate aerosols, which are quite cooling. So air quality policy may actually enhance greenhouse gas, may in fact enhance radiative forcing. If we repartition that one step further, though, we can see that it's slightly more nuanced message here. That, OK, we've got the air quality pollutants, such as aerosols here, but we've also got, in this positive forces here, we've got things like ozone and black carbon, which we could also control under air quality policy. And to a certain extent, oh no, not on this one, and to a certain extent, methane. We talked extensively about methane yesterday, and I'm not going to do it again. It's got a relatively short lifetime. Whether it's a long-lived greenhouse gas or a short-term rated forcer, I think you could discuss. Actually, though, methane chemistry, as we saw yesterday, is strongly linked here to this. So you get a double benefit from reducing methane. You reduce a direct forcer, but also you reduce one of the prime sources of ozone in the atmosphere as well. So you get what's often referred to in the business as a win-win benefit from controlling these two. So there's been a lot of people thinking about, could climate goals be achieved at least partially by non-climate treaties, by actually thinking about air quality pollutants in a sensible way, and can we actually think about putting those together in a way where we can get these win-win benefits. Now, I haven't put the slide in, which I have, and I've just put an article out actually with a colleague of mine looking at how one could think about the win-win benefits of air quality and climate and what the trade-offs are. And it's quite a complicated area. I already just told you about sulfate and the effect that they have, but you've also got to think about when you're implementing policies, are they win for air quality and win for climate? Many of them are actually a win for climate and are detrimental to air quality. Yet, if you're driving at air quality, you've got a human health imperative. I mean, Guy showed some slides in his talk last night of China. There are many, many people suffering from very, very poor air quality. It is an imperative that they sort that out for human health. Yet, it will have significant impacts on climate also. So one of the things that this report looked at, this is a well worth reading integrated assessment of black carbon and tropospheric ozone, is it looked at whether you could use a methodology of thinking about these short-term forces, as they're often called, short-lived climate pollutants, short-lived climate forces, at the same time as doing CO2. So what they showed here is that you put the CO2 measures in, you would exceed it, where if you actually put the CO2, the methane, which I talked about, that win-win benefit, and black carbon reduction, you would actually be able to slow that rate down. And that's a combination, really, of you have to have the CO2 reduction, but that's something that occurs over a longer time. With these short-lived climate pollutants, you've got a one-off chance. It's a one-off chance. Once you've reduced them, you're not going to be able to do it again. You could actually reduce their climate impact. And there's a very good review on black carbon chemistry and the uncertainties involved in that just came out at JGR at the beginning of the year. And I can talk to you about detail if you're interested in the science behind that. So, but I just want to trigger this idea that you could think about in the climate context these short-lived climate forces. But you've got to think about the air quality benefits or disbenefits and the climate benefits or disbenefits and trade those off as well. So some very interesting questions there. And we need good, sound science to base those impacts and mitigation on. And that's a challenge in itself to everybody. I want to move on a little bit now to talk about another area. I've talked a little bit about NO2 as a major pollutant. One of the biggest pollutants also that's a major problem in Europe and around the world is particularly fine particles. Fine particles are these ones down at the smaller sizes here, typically less than around 2.5 microns to about 0.1 microns have been shown to have the largest health effect. If we go back to looking at what the typical sources are for those in an area, I'm sorry, this is kind of a UK-centric view. Many of those particles come from things like road transport emissions, residential combustion, and so road transport is a big. There are a whole bunch of others, and they are predicted to decrease in the future. I read a very interesting article this week that was claiming if you go forward about a year, actually it will be the non-exhaust emissions of particles that will be the most important source of these small particles. And you go, non-exhaust emissions. Yeah, what actually it is is that it's the tyre and brake wear that's abrading these particles on the road surface. And actually, these particles are then resuspended. So it's not only the ones coming out of the back of the exhaust pipe, it's actually from running the cars on the road. And this presents a real problem for mitigation. And actually, in a few years' time, it is more than likely that those sources, the resuspension sources, will be dominant over the end of tailpipe emissions. We really have reduced very well what's coming out of tailpipes. And I should tell you one story very briefly about mitigation. The Mayor of London was really worried about this resuspension problem, so he decided to mitigate it, and he decided to mitigate it near the monitors in exceedance, which is not really the thing you should do. And the way that he did it was he glued the particles to the surface. So what he did is, have you ever done papier-mâché with flour and water, and it kind of makes a very weak glue? What he did is he employed some people to go out spreading flour and water on the road, essentially to glue the particles to the surface. And flour and water, of course, is very biodegradable because it can wash away, but it actually didn't have that much effect, interestingly enough. So it's quite an interesting problem about how you get rid of these very small particles. You can't glue them to the road, apparently. I think what's amazing about these particles, and I guess this is because I'm a gas phase chemist and I spend all my life thinking about gas molecules, and I showed those pictures of CO, floating around the world for long periods of time. This is just a picture of PM 2.5 measured by windroses in the UK, and you can see the direction that they're pointing. Where are they pointing towards? The Netherlands, yes, the Netherlands. And these are some source receptor type modelling. And what you can actually see, and I think this amazed me for particles like, so these are particles smaller than 2.5 microns. They do travel significant distances. They can travel hundreds and hundreds of miles. I wrote in the report recently, nobody liked it. I wrote a report, they are gas-like, these very small particles. So I think it's, I think that was a real realization, for me at least anyway, that these particles, a bit like a gas molecule, can actually go significant distances. They're very complicated as well in terms of their origin, in terms of their chemical composition. Moving towards the health sphere, people in the health sphere would really like to believe that, that you could identify silver bullets, the chemical component in these particles that leads to a health effect. But all the evidence today says that it's just the particle mass that is the critical thing. So, the particle size that is the critical thing. It doesn't matter what the particle is made of. The evidence is very, very conflicting once you try to get down to that sort of level. And the EU is undergoing an air quality revision at the moment and is saying really it is only the particle size, 2.5 microns, which is what the current legislation says, that is important. But yet, there's a great deal of chemical differences in these sort of particles, from all the way from inorganics, sulfates, nitrates, ammonium, all the way through to complex organics. Yet, the health effect seems to be related to size rather than composition. If you look at some typically small particles and their composition, this is in urban. You can see here that mostly here that they're nitrate, sulfate, these are the organics here, and then some sort of other salts, including some elemental carbon. When you have episodes, they can change greatly. In this episode here, you get a much larger amount of nitrate during an episode of more than 50 micrograms per meter cubed. So, the composition of these particles does change. It is complicated, but their relationship to health effect is unclear. The other thing to say is that if I want to control these particles, there are a range of sources. Each one of these is a different source that I have to think about controlling. And actually, it turns out that some of these organics here, they're actually natural. They're coming from oxidation of natural compounds. Well, how do I control those? Do I chop trees down? Probably not. And actually, here's some experimental data which supports that. This was where they actually flew an aeroplane around London, measuring the particles. And so exactly, in a sense, the same experiment that I just showed you with the model. And they looked at the amount of these particles on the way into London, on the way out of London again, and actually they could verify, if you look at these numbers in some detail, you could then verify that exactly the same sort of thing I was talking about in the model a few minutes ago was absolutely true. you can then use the composition of those particles to actually relate it back to source. So I said they have different composition, and that therefore, because they have different composition, you can actually use that composition to work out which source they might have come from. So you can verify all the way back to your emission inventory, which can be very important. You want to understand whether your emission inventory is right, because a lot of your policy-making decisions and a lot of your mitigation strategies are built on whether you believe your emission inventory. In this case, you can work this back here, and you can show that it's approximately about right. So that's a kind of taking you into the issue of particles. There's a great report from the Air Quality Expert Group in the UK available, which takes you into a lot more detail about the regionality of these particles. We get, in the southern UK, 60% of our particles from the French, the Dutch, and the Belgians. Presumably they get the same amount from us as well.
It's garlic.
It's garlic. OK, so nonetheless, what other issues do we need to think about in air quality? I've talked a lot about small particles. There are civil disasters here. This is a fire that was in the UK a few years ago at a place called Buncefield. This is a satellite image. You can see the smoke coming off. I think it's actually going this way. You can see the smoke coming off Buncefield. Luckily for us, it was a very, very hot fire. And that lofted all the pollution actually quite high. So it actually never grounded and went out to the sea before it actually grounded onto the surface. But sometimes we need to be able to understand the dispersion of pollutants in a very specific way with respect to air quality. And actually, it was, this paper says it all here, it was an extreme accident without air quality consequences, which is quite interesting in that sense. Other topics that are of real relevance in the air quality area are ship emissions. It is predicted by the year, let me get the year right, 2030, that for sulfur dioxide and to a certain extent NO2, there will be more emissions out at sea, which is unregulated or not regulated in the same way, than will be from land sources. So in fact, actually, shipping emissions, particularly in the northern Europe again, is actually quite important. And this is a beautiful satellite image from the Bay of Biscay. Just can't quite see where we are. We're somewhere down here, aren't we? You can actually see all the ship trails in the clouds there from the particles coming out of the back of the ships and the water's condensing on them to produce the ship equivalent of a contrail. But you can see them all across the Bay of Biscay here. All these ships. The main shipping lane runs obviously across here and into the southwest approaches into the UK. And you can actually pick these ship tracks up from space. This is some NO2 pictures. And you can see here the main shipping across here around India, up through the Suez, across the Mediterranean. Again, you can see the coastal things here. And you can see that actually ships do tend to go in lanes. And I think John has some very interesting slides that show that these shipping routes will actually shift owing to things like piracy. So John can actually detect piracy from space, which I think is a very clever thing to be able to do. But it's interesting to note that these ship emissions do have an impact. So 87,000 deaths per annum have been estimated from just those ship emissions alone. And that can particularly you can see the hotspots from where these ship tracks really are. And the European Environment Agency has put out a major report on thinking about the next level of control for this. And there are what are called seeker zones where you look for reducing the fuels that are used by these ships to low sulfur fuels. Because essentially ships, once you get out of low national waters, essentially can use unregulated fuel. So they just burn any old stuff, the cheapest fuel that they can actually burn. Sump oil, as it's called. I don't know what the translation to other languages is, which is absolutely grim, which is presumably why you get the ship tracks as well. So ship emissions is an issue that's coming onto the air quality agenda, and understanding offshore emissions as well as onshore emissions when you come to think about air quality impacts. Another one is in the area of biofuels and biomass burning. We have something in Europe called the renewable RTO obligation, renewable something obligation, which is to increase the amount of biofuels actually in our petrol. So typically if you go and buy petrol or you go and buy diesel, 5% of that is sourced from a renewable source. Typically things like palm oil or biodiesel is actually a synthetic thing. And actually the biofuels, and this is again a very interesting confluence between climate change policy and air quality. I mean, a lot of these have been produced because in a sense they are not using fossil carbon. You're replacing fossil carbon with current or contemporary carbon in theory, so therefore you're not doing pollutants. You can see here you then put these biofuels in. Is anybody from Brazil? Anybody from Brazil? No. In Brazil, they have such an excess of sugarcane. They actually, in many of the cities, use bioethanol as a major fuel source. And you get very, very different air pollution characteristics if you use these very high-strength biofuels. So 85%, typically 85% or more. You don't tend to ever use these things on your own. You always tend to mix them with a little bit of petroleum. So even bioethanol that you use in Brazil tends to be 85% ethanol and the remaining normal sort of petrol. And actually, you know, there's a whole bunch of questions about whether you should use these sort of compounds or not. But nonetheless, they do change the VOC to NOx speciation. They change what comes out of the back of cars. We did a little study for the UK government that showed that actually, according to the best evidence, these very weak 5% or so doesn't seem to change the amount of particles or NOx that you get out of the back of these cars. But these biofuels are an issue and how they're going to be introduced. But there's huge issues about whether you should stop food growth to buy biofuels, their impact, particularly in Asia, where you've got great growing of palm oil. And there's whole issues really about this contemporary burning of contemporary carbon as well. There's been a growth in biomass burning boilers. So again, rather than burning gas or burning fossil fuels, many households and schools, etc., are moving to burning wood. Now, what we do in the UK, for some bizarre reasons, we import it from Canada, which seems a little bit bizarre. But after spending years trying to remove NOx from the urban atmosphere, what we're doing is we're putting these biomass burning boilers in again, because it's all in the name of climate change, reducing fossil fuel burning, and we're burning wood. So there's lots of questions around these biofuels and their use. And there's many ethical questions, and there's many scientific questions as well. And I don't make a judgment about whether it's right or wrong. I think our job as scientists is to look at the scientific evidence and help advise on the best way forward. Fracking, here's another one, which is just coming on to the agenda. I mean, fracking is widespread now in northern US. It's driven down and massively revolutionized the energy market. In a sense, it's driven down fuel and energy costs massively. It may well have an impact on renewables, because renewables will now be more expensive than cheap gas that is available from fracking. Fracking has potential environmental impacts in terms of fugitive emissions of methane, and also emissions of methane into groundwater, and the effect that they may well have. But also, it may well have air quality implications. And I don't think anybody really knows what they are. I just chose one study from the Colorado group who linking fracking to higher concentrations of air pollutants. I think it's entirely possible. I mean, they're talking about in the UK, potentially we've got 360 trillion cubic meters of gas available in our shales. That's a lot. And you know, that could really change the way that it is. And the push to energy and energy demand is really going to always overcome air quality. So I think that's a breaking issue, if you'll excuse the pun, fracking. And we've got to think about how, in the air quality area, we'll respond to that challenge. I know that Claire was telling me about some work they've been doing looking at flaring in terms of this as a source of air pollutants such as black carbon. And not directly from fracking but from gas use anyway, and that's actually quite significant. We always want to think about verifying and testing. This is some work that John's team did, which I really liked, looking at how you can use space data to challenge emissions. It's very important if you go to, as I said earlier, get your emissions right. You need to verify and test those emissions. This is a great story where actually when they first tried to publish this paper, it was so radical in what it was suggesting that it got rejected until actually they went back and looked at the emissions and realized that actually the space was right and what they'd been doing was wrong. So what you can see here, here's France on the left, the satellite data here showing the decrease across that and the different emission inventories. Here's Germany, here's Britain. Actually, it suggests that actually a number of us here, particularly in France and Great Britain, have been probably overestimating our emissions. We've been actually saying we're putting out too much. There's a little bit of a different story in Greece. Sort of predicting it going down, it seems to be going up. Italy, anybody from Italy? Yeah, look at this. So very flat, and Spain actually going up as well. I won't ask if there's anybody from Spain. So actually you could use these sort of things, and actually John and his group have driven this down to being able to look at this at a city scale. So you can actually not only get for the regional levels, you can actually look at that, and you use the satellite data in combination with a model, and you can actually look at the city scale emissions, and that's a very good way of being able to challenge these emissions data, which is so important for understanding our air quality policy. Moving out to sort of some kind of bigger ideas to finish off, and some of the bigger challenges that we face moving forward in the kind of air quality context, kind of reaching out. This is the concept of planetary boundaries. Again, Guy, in his talk last night in the town hall, made it very clear that one of the biggest challenges we face moving forwards is the idea of sustainability. We've got to move to a more sustainable way of using our resources on our planet. And I guess that exactly moves to all the issues that I've talked about. Air quality sits at a nexus of many of those issues. It sits at a nexus of how you use energy, how you use transport, how you use resources to support all those. And actually air quality is a manifestation, really, of that sustainability issues. This is one thing that came out a few years ago by Johan Rockström, looking at planetary boundaries, looking at the way that you could actually quantify these boundaries, and recognizing that we in a way need a more holistic way of dealing with all the different things that are going on and quantifying that. Now there's some people that like planetary boundaries, there's some people that don't like them. The idea that there is a boundary and when you cross it there is a consequence is a little bit of a problem with approach. There isn't, you just can carry on once you've crossed that boundary. But nonetheless, it's a very interesting way of thinking about the way that we can move forward and put these issues together and begin to look at policies and measures that join them up in some way. And I think that's the Earth system challenge really at the centre for the next decade. You've heard questions about urbanization, and urbanization is a key thing. 70% of us in Europe live in cities. Around the world, 2008-9 was a momentous occasion because for the first time in human existence, more people lived in cities than they did in the rural countryside. So we as a planet have changed. We now, more of us live in cities than we do. Now, actually, before you go, you might jump to the conclusions, oh, living in cities is bad environmentally. Actually, living in cities in some respects is a very good idea. It's much more sustainable in terms of resources. You're not using huge resources moving around. It's much more compact. You can recycle more easily. There's a whole lot of things you can do in cities much better. But there are, I think, demands for thinking about the impact on things like air quality and many other issues that come from this in urbanization and industrialization. if you think about the sustainability question in urbanising, I think this is a very interesting set of stats that Karen Sato came up with. John mentioned this morning that by about 2100 we'll have another 3.2 billion people if we top out at around 10 billion. They'll be mostly in cities of 1 million. That will require 3,200 cities of 1 million over about 89 years. 89 years is that many days. So 3,200 cities over 32,000 days will need about a new city of 1 million every 10 days. Now, that's a calculation which you can debate with me. I'm quite happy to, but I think it shows you the challenge that we have. If you put 3 billion people on over that time period, where are you going to put them in a sustainability context? You know, are you going to build cities and be able to respond at that rate to the challenge? What impact will it have on things like air quality? There are other issues which I want to mention in passing. I've talked a lot about ozone and methane over the last couple of lectures. Nitrogen, as I said yesterday, is a key issue. I think one of the challenges for nitrogen is that actually, if you look at it, it repartitions all the way through the system in very different ways, and it's a real challenge to track that. So actually there's now a big call, and there's a great review called the European Nitrogen Assessment, which I would recommend that you had a look at. But the question now, in the same way that we look at carbon and carbon trading, should we be looking at nitrogen and nitrogen trading? So much in our food, there's a lot of embedded nitrogen. So we're actually using somebody else's nitrogen when we import food from somewhere else. And nitrogen is a sustainable resource. Also, we talked a lot about the air quality impacts of things like nitrogen oxides, also ammonia in terms of aerosol. So do we need a new way of thinking about nitrogen and nitrogen flows through the system, through the atmosphere? Because actually, when you have a cascade like this, you may actually, abatement may actually swap one pollutant for another in this system. So you might think that you're solving a problem, but in fact, all you're doing is you're shifting it to a different compartment in the Earth system. This is a slightly complicated and wordy overhead, but actually it looks at the question of when you've abated things in terms of nitrogen, do you get the benefits that you would expect? So actually, it is a real challenge in the nitrogen and nitrogen impacts area. There are other things that we've got to think about also as I begin to wrap this talk up when we're talking about air quality. There are external factors. There is demographics. We in Europe are an aging population. I'm speaking to the youth. You're the future old people. I'm an old person now. Demographics will be a key issue when we talk about the impact of people's health on an aging population and air quality. We maybe have to consider demographics and the effect that will have. And actually, you'll see an aging population. One thing that I want to reinforce about this is that sometimes the difficulty with air quality, and actually you heard it in the discussion after the talk last night in the town hall again, becomes very local. It comes about, I think the discussion, if I picked up part of what it was about was whether such and such a monitor in Bayonne is not as good as such another thing in Bayonne, and it becomes a very local issue. But it is a global issue. And there's been a big work in the UNECE task force on the hemispheric transport of atmospheric pollution and how much pollution you actually have control of, how much are you actually importing into a different country. And here's a very famous paper that looks at the growth of ozone over a period of time. So if you go back to the turn of the century before last, I guess, around 1900, there were some measurements made at Montsouris in Paris when everybody thought ozone was good for your health. They were making good measurements of it. And ozone, before the Industrial Revolution really kicked in, was at around 10 ppb. When we started measuring it again in the 1950s, it sort of doubled to 20 ppb. And typical background levels today are nearly 4 times what they were in 1900, around 40 ppb. So actually, we've had that growth in ozone. And actually, the air quality standard is around 40 ppb, and that actually means that the background ozone that we're now importing hemispherically is going to drive the exceedances. So we actually need to work across those sort of bigger scales. And you can see the sort of trends here. This is the Pacific trend in blue and the Atlantic trend in red there in the growth of ozone. And it's quite clear. This is a beautiful map, I think of beauty. This is an infrared satellite image with CO trace context. You can see the way that pollution just flows out. This is the CO in red here, coming out the US seaboard here, being transported towards Europe, and then actually it hits a weather system that, in this case, pushes it further to the north. So actually, we do get this transboundary air pollution, and we must kind of think about it in the larger context as well. Okay. And these are actually some of the numbers that are from that HTAP exercise. There are things that we haven't thought about. There's a whole sorts of interesting chemistry coming to the fore. This is some chemistry on we're realizing that in the US here you have air-sea interactions, so you can get that chloride coming from the sea salts mixing with the pollutants, and there's lots of widespread interest now in a compound called nitrile chloride, which may be a missing oxidant in the atmosphere. And so you have to think about how to couple these different partitions together in their system. So air quality is not a problem on its own; it's a coupled wider problem as well. So finally, to think about mitigation, what are we doing about this? We talked a lot about what the issues are. At European level, we have the Ambient Air Quality Directive, or the Air Quality Framework Directive and daughter directives. And what that does is set up a series of monitoring and reporting limits for air quality. This is just a list of them. I don't expect you to assimilate them, but they're for particles PM10, PM2.5, nitrogen dioxide, and ozone. And there are 24-hour means and annual means that one has to get. There are dates for achieving those. So we have a series of structures to allow us to understand how well we're doing, a series of target or limit values. We have a myriad of policy tools, probably about 3, Gothenburg Protocol, NECD, and the Ambient Air Quality Directive, which all target different parts of the story in Europe. We have these systems that we've put together to measure them, all the way from roadside sites here. This is what the current network in the UK looks like, all the way to research stations. This is Mace Head in Ireland, which is very important for understanding the import into at least northwestern Europe. So you do have to measure air pollution. Modelling has a key role to play, particularly in the predictive area. Also, in a way of being able to spatially map these things out is very important as well. But nonetheless, measurements retain that kind of background. We then have to take it down to that predicting sort of level. This is actually the city I come in again. How much will somebody be exposed? I live just out this way. But you can see many modern cities all funnel down into the centre. So you get air pollution, particularly at the middle of these cities that were especially expanded in what we call the Victorian era in UK. So that was very quick on mitigation. To finish off, controlling air quality. Can we control the air that we breathe? We do have pollution controls. We have brought in a whole bunch of measures. And they run from the technical measures, which have been reducing things like NOx with tailpipe measures, to using cleaner fuels, which I've talked about. It's very important also to improve vehicle inspection programs to make sure people are doing that. But also there are a bunch of things that we call non-technical measures, and we're reaching a limit now where we have to encourage people to do more non-technical measures, and a lot of that is to do with behavioural change. And that's quite difficult for a physical scientist to deal with, asking people to ride bicycles and that sort of thing. But it's an area that we're now reaching, because a number of the technical measures that we're getting to are coming to their end. You really aren't going to be able to reduce what comes out of the back of a car much more than it is. I mean, it is actually a very clean beast as it was compared to being 10 years ago. It might be that we have to move to electric cars, really, as the next, or hybrid cars as the next way forward in this area. And there's no doubt that one of the reasons, though, the world air pollution has changed is actually the Euro standards. This is the Euro standards for air pollution have been have been implemented around the world. We're just now moving to the implementation of what's called Euro 6 up here, but many of the countries around the world are implementing the Euro standards for air pollution. That's been a very strong mitigation measure. And this is just the European Environment Agency assessment of what's going on, and showing that actually for particulate matter there was a 30% reduction at the end of the last decade, and showing where the major sources have come down. So we are actually, as I say, some of this is working. And the future, if you look at it, does show that it will remain a problem. This is without climate change. This is just with current mitigation mode. So here's a 2000. This is a loss in life expectancy with respect to PM 2.5. And you can see that the red zones are decreasing. Bit of a problem here again, nonetheless. Hey-ho. But you can see that the predictions are, if we manage to implement these sort of things, that there should be a brighter future. That's a model result, though, and what is absolutely true that is that it's actually not all going as we predicted. With respect to NO2, there are still problems and it's bottomed out. With respect to ozone, the average number of exceeding stays isn't really changing, and we've got that problem with the background interaction with the regionally produced ozone, which is a challenge. I would like to just, if I may, give two more overheads, and the two more overheads is that I think a role that we have to play is, as scientists, is in this evidence-based policy making. I think we've got to be giving the policy makers good solutions and good scientific information with good estimates of uncertainty, so that they are able to translate our scientific understanding into good air quality policy. So, Claire's told me I've got to finish. So how clean is the air that we breathe? I think there is a good story there. Actually, many pollutants have decreased under legislation. There are continuing problems, though, that we need to think about, particularly with respect to exposure to particulate, acidification, and ground level ozone. I think there are also challenges in the area of climate change and the coupling to climate change, and thinking also about sensible climate change policy along sensible air quality policy. I think I want to finish with maybe, there's an up note and then a down note. I want to finish with one thing. This is something that I saw out of an OECD report that came out just last year in March, and it said air pollution will become a bigger global killer than dirty water. And I thought that's a very telling fact, that if you think about the way that a lot of policy has gone globally about providing people with clean water for health, another great global commons in that self, actually by 2050, air quality will be a bigger potential killer than dirty and unsanitary water. So I think there's a challenge for us all there to understand how we can help that problem with our models, with our measurements, pulling those together to think about developing policy, developing better predictions and verifying those with a range of observations. Thank you very much indeed.